Hi everyone. Today we're going to look at the first day of our regression unit. And the way we're going to start looking at regression is by reviewing scatter plots. So if you think back to Algebra 1, we spent some time looking at scatter plots of linear functions. And what a scatter plot is, it's just a graphical display of data comparing two related sets of data. So we look at scatter plots to see if there's any pattern or trend or relationship between the sets of data. Now, when we talk about correlation, it's the way that points are situated on the graph. So are they related in a positive way? So if you imagined a line that could possibly, get as close to as many points as possible, if that line appears to be going in a positive direction, this would be data that has a positive correlation. If the line had been sloped in a negative direction, as x got bigger, y got smaller, we would call that a negative correlation. And if the data was spread out to the point where you really don't think you could put a line, either positive or negative, to kind of capture the majority of the data, then we would just say really there's no correlation because we really can't represent it with a line at all. Now, when studying linear regression, there was a value that you spent time looking at called a correlation coefficient. And this number is just used to measure how well data matches the line that would best fit it. So how close is all of the scatter plot to that line? And we used to call that the line of best fit. So if you look at the data in this scatter plot up here of weight versus height, you can see that majority of this data is not very close to the line. So this correlation coefficient number is going to be a number between -1 and 1. And the closer it is to positive or -1, it really shows us that the data is going to be really, really close to that line. And the closer this number, this correlation coefficient is to 0, it's really telling you that there's no correlation at all, or maybe a weaker correlation. So the way that we can look at this is if you look down here, again, we're going from a range between -1 and 1. So let's say we had an R value. I'm going to look at these scatter plots below. So if I was looking at this scatter plot here and I wanted to draw a line that got really close to them. Now, my highlighter is a little bit thick here, so if I made that a little bit thinner, let's say, I'm not going to necessarily get every single point, but I have almost every single point. So I might say that this is a correlation coefficient. Now, when we talk about correlation coefficient, back in Algebra 1, we use the letter R to represent that. This might be an R of, 0.98, let's say. Again, I'm just approximating. It's not exactly 1, because if it was exactly 1, we would call that a perfect correlation, a perfect positive correlation, which would mean every single point would fall on the line. But it's definitely a strong positive correlation. Now, if you look at the second example here, you can still tell that this is positive, but now the scatter plot is even further away from that line of best fit. So maybe that would be an R, I don't know, of maybe 0.65. So it's definitely still positive, it's still correlated, but it's not as close to +1. Now this middle graph we would say has an R of 0 because there's no indication that this data has a correlation either in the positive or negative direction because the points are so scattered, there's no real shape to that graph. Now I can see here these points are definitely trending down in a negative direction, but again, the points aren't as close. So if I was kind of mirroring this to my moderate positive correlation, this would just have a negative in front. So again, not that they're exactly the same, but I'm just going to use my same value, maybe -0.65. And then again, this one is much closer together like our first graph, so maybe we could call that a correlation coefficient of -0.98. Again, just making these numbers up, but using my scale from -1 to 1 to justify, what I'm calling them. Now, the line of best fit, again, that's just that straight line that you would say best represented your scatter plot. Now, in Algebra 1, you spend a lot of time looking at linear models, but in Algebra 2, we don't really spend as much time focusing on linear. We look at many other types of functions. So when we get to regression, and all regression is just a way to predict things using the functions that we know. So is the relationship between these two sets of data linear? Is it logarithmic? So does the scatter plot resemble a log graph, which is a function we studied this year? Does the scatter plot resemble more of an exponential relationship? Power is more of the umbrella term for all polynomials. So if is it more quadratic or cubic, is x being raised to the fourth or the fifth degree? So that would be a power relationship, but I would say quadratic and cubic you would see probably more often. And then sinusoidal is, again, we used that term to be the umbrella term for sine and cosine. So sinusoidal is the relationship more cyclical. It rotates, it hits mins and then maxes and comes back down to mins and rotates more along a sine or cosine curve. So what I would like you guys to do, now that we've just looked over the types of functions we studied this year, I want you to take a look at these first 5 questions. Now I know I'm not really helping you yet, but I want you to pause the video and I want to just see if you can read through these 5 questions and do your best with each of them, and then hit play and we'll go over them. Okay, so hopefully at this point you've taken a couple of minutes to try these questions, because they're not really questions I can teach you. As long as we've reviewed some of these topics as far as the functions we've studied this year and what a scatter plot is, and what correlation means, you just really had to give these a try. So number 1 says, Samantha constructs the scatter plot below from a set of data, and what we're being asked is, based on her scatter plot, which regression model would be most appropriate. So we're thinking we have exponential, linear, power, and logarithmic. So what I always like to do is try to kind of sketch something that would go, as close to through all of my, points as possible to get kind of in the middle of them. So I would definitely say this is not linear or exponential. And as far as power goes, it doesn't really look cubic or quadratic. This is definitely similar to a log graph. And if you wanted to right now, you could go back up to what we looked at up here and really see that, yes, this definitely started around that 0.10 and went up and over to the right like a log graph would. And you could always type in log x into your calculator if you wanted to just confirm that that definitely resembles a log function. Okay, question number 2 says, which value of R represents data with a strong positive linear correlation? So again, we have to remember that that R value is going to go between -1 and 1, so it's not going to exceed it, so we can get rid of choice 3. If it's the strongest positive, we're looking for the number closest to +1, and that would be choice 1, 0.89. Number 3 just says, which could be the approximate value of the correlation coefficient for this accompanying scatter plot? So I would say it's definitely positive, it's strong. It's not perfect because not everything is touching that line, but it's going to get really close to 1. So 0.9 would be the best resembling that scatter plot. Okay, let's go back up to number 4. So the points in the scatter plot below represent the ages of automobiles and their values. Based on the scatter plot, it would be reasonable to conclude what? That age and value have a coefficient of correlation that's less than 0. So let's just go through each choice here. So is our correlation coefficient less than 0? Is it equal to 0? Is it between 0 and 0.5? Or is it greater than 0.5? So if we look at this, again, if I'm thinking a line that would kind of capture the majority of this data, it's definitely a negative correlation. So it's not going to be equal to 0 because that would be no correlation. It's not going to be greater than 0.5 or between 0 and 0.5 because those would both be positive. So it has to be choice 1, something less than 0. Okay, and then question 5 gave you data again to analyze. The price of a postage stamp in the years since the end of World War I. And they're giving you years and price as far as your x and y values. They want you to find the equation below that would best model that price of a postage stamp. So now we're looking at 4 different functions, or actually 4 different choices of functions. Choice 1 is a linear function. What I'm going to do is I'm going to go up here real quick and just kind of sketch this function, try to capture the majority of this data. So if I'm looking at my sketch, I would say this does not resemble a line. It also doesn't resemble a sinusoidal curve where I have the, the cyclical nature of sine or cosine. So because it's not linear or sinusoidal, I would definitely be narrowing it down to 2 and 3 because this does appear to be exponential, right? If we just kind of review what that would look like, my exponential functions. So now we have two choices. So the best way to kind of decide between them is to type them into your calculator. So I'm just going to get my calculator. Okay. So what I want to do right now is I want to type in the first one. So, or choice 2. So let's go to our y equals. Let's type in 1.04 times 1.43, raise it to the x, and let's go to the table. Okay, so now on our picture, so we're looking at these values. If you're looking at your notes, I can see that there's a point, the y-intercept looks to be a little bit above 1. So let me go back one in my table here, and I would agree that's 1.04. That makes sense. And then if you look at the second point, so if I just go back for a moment, if you look at that second point, this point appears to be, maybe somewhere a little bigger than 10. Let's say maybe it's 15, and somewhere around, I don't know, a little bit bigger than 1. So I want to kind of use that as I look at my table. So that point, or even if you wanted to use the point 40 comma, maybe this is 40 comma 5. So let's go back to our table and let's scroll a bit. So if we go down to 15, we thought where we should be somewhere around, I don't know, 1 or 2. We're already up at 222. And then not that I really need to do this, but if I went all the way to 40, I'm just going to jump to 40. Yeah, now we're already way, way beyond 5 as far as our price in cents. So I'm going to go back. At this point, I'm pretty sure it's choice 3, but let's just confirm it. So let's type in 1.43 times 1.04 to the x. Let's look at this table. Now 40 is around 6.86, and I said what it looked like it was around 5, so that's much closer. And then let's go back to 15. And 15 is around 2, which is exactly where our graph looked like that plotted point should be. Now the reason, another thing you could have looked at here just to kind of determine this graph is not growing that fast. As I'm 0, 20 years out, 40 years since World War II. It's growing much slower, meaning the base of it should be a number smaller. This number is almost 1.5, so, or 1.43 is like a 43% growth rate, whereas choice 3 only has a 4% growth rate. So that definitely looks like it's a slower growth than choice 2. So that's how you would narrow down to number 5. Okay, so now we're going to look at a couple other questions involving regression. So for number 6, what I need everyone to do at this point, if you have not taken your calculator out and you just kind of watched me go through the last one, you definitely need your calculator out for the last 2 questions. Today we're just going to look at questions 1 through 7. So we're just going to do 2 more together. You'll complete homework 1 after this video, and then the next video we'll go through the remainder of the notes. So for question 6, if everyone could get out their calculator, we're looking at a question that's talking about a cup of soup. It's being left out on a countertop to cool. So time in minutes is X, and the temperature in degrees Fahrenheit over the time is Y. So over 10-minute periods, they're giving me from 0 minutes to 10 minutes. They want me to write an exponential regression equation for this data. So first thing we're going to need to do, and if you haven't worked on regression since, Algebra 1, it's probably been a while. I'm going to come back to my calculator. We're going to need to go into our lists. So we need to type this data in. So everyone's going to click Stat and then Edit. Now to save time, I already went and typed this in, but all of you should have blank lists. So what you're going to start doing is you're going to just go to the bottom right here, the top of list 1, right below L1, and you're just going to start typing in the numbers 0, 2, 4, 6, 8, and 10. You can scroll by hitting enter between each one. You can just see now that I'm kind of typing over these just to show you how to get around. And then you can just scroll to the right, and that would bring you to the top of L2 since you don't have data in there. So take a moment to type all of that data in. And once you've typed it in, I want you to go back to Stat. And now we're going to calculate an exponential regression equation using our data. So you're going to go over to Calc. So we still went to the stat menu, but now we're over into the second column where it says calculate, and we're going to go look for where it says exponential regression. So this is going to be choice 0. So our X values, our minutes, are in our L1, that's correct. Our Y values, our temperature in Fahrenheit, is in L2. We don't need anything in frequency. We don't need to store this equation. We're just going to go down to calculate and hit enter. And the nice thing about these regression equations is not only do they give you the standard form, well, they give you the values, but they give you the standard form. So they're telling you exactly what to do with A, which is 180.3768, and B, which is 0.95386. A is your leading coefficient or your y-intercept of this exponential function, and B is the base or the multiplying factor. So let's go back to our notes and let's write these values down. So when you're calculating a regression, it's always a good idea to kind of remind yourself. So we put all of this data into our L1, all of this into our L2. To get to our lists, again, just to remind yourself, we did stat and then edit. And then we went to stat, calc, choice 0 was exponential regression. Okay, so we ended up with an A value of 180.37687 and a B value of 0.9538696. So they want me to write this regression equation rounding all my values to the nearest thousandth. So again, they told me how this equation should look. So now I just need to round appropriately. So 180 nearest thousandth means 3 decimal places. So I'm going to round that 6 up to a 7 because of the 8. And then times 0.954. Again, I'm rounding up the 3 because of the 8. And then I just have to remember to raise that to the x power. So that is the answer to the first part of this question. We wrote the exponential regression equation and we rounded appropriately. Now we're being asked to use our equation to estimate to the nearest tenth of a degree the temperature after 1 hour. So 1 hour, we're not using hours actually in this question. All of our time has been in minutes, so we're just going to need to think about that in minutes. That would be 60 minutes. All right, so this is just the plug-in. 180.377 times 0.954 to the 60. So go to your calculator, type that in. I'm not going to show this, just everyone type this in, 0.954, raise it to the 60. And you should get the number 10.69260791. So to the nearest tenth of a degree, it's 10.7 degrees Fahrenheit. Now, if we were in class right now, I would have everyone pause. So I'm just going to continue on. If we paused right now, I would be asking you the question, does this make sense? So you have a cup of soup. Just put the words cup and soup together, sorry. So you have this cup of soup, and it started out at 180 degrees Fahrenheit when you first put it on the countertop to cool. After 10 minutes, it was around 110 degrees. If you left this cup of soup out on the countertop to cool, it's in a room, right? So you would assume maybe your house is set to, 67 degrees Fahrenheit. So at some point, this cup of soup is going to reach room temperature, and unless you put it in a refrigerator or a freezer, which it didn't mention here, you wouldn't expect the temperature to really get this low, to get down to 10 degrees. So something that's just worth mentioning right now is sometimes regression equations are appropriate until a certain point, and they're only a good fit until that point. Even though this function would say that the temperature would reach about, almost 11 degrees after 60 minutes, that doesn't really make sense in the context of this question. So we just kind of put this here to talk about how regression sometimes makes sense, but you have to be ready to analyze when, even though the function gives you a certain value, it might not make sense in the context of the question. So this does not, make sense unless they told us, then all of a sudden this soup was put into a freezer. Then this number would make a little bit more sense. Okay, And then we're going to use this equation to estimate how long it would take for the temperature of the soup to reach 80 degrees. So now they're giving me a temperature, so that's a y value. So I'm going to set my equation equal to 80. And I'm going to solve for x. So if we're solving an exponential equation, we have to isolate the base. So let's divide by the 180, 0.377. So if you did 80 divided by 180, 0.377, you get 0.44351. I'm just going to approximate that for now. Leave the full number in my calculator, but I'm not going to write the whole thing out for now. Again, do not round until the end. Now we have a base raised to an unknown set equal to a value. So let's use logs. So if you circle the base, run the race, go around the equal sign and back. If I rewrite this equation now in the equivalent logarithmic form, I would have a log with a base of 0.954 of this value, 0.44351, equal to x. Now you can type this in. Let's go back to my calculator, just so I remember how to do this here. So I'm going to type in alpha y equals enter. Oh, sorry, alpha y equals 5. Okay, my base was the 0.954, and that number we had, the 0.44. Notice how the whole value is still in my calculator. I'm using the entire number. I don't want to round. Hitting enter, we get 17.26469. Let's go back. And we're being asked to round this to the nearest 2646, to the nearest tenth of a minute. So after 17.3 minutes, the soup is going to reach 80 degrees. Okay, and let's look at one more question for today. We're going to look at number 7. So for question 7, again, we're given a table of data. This data is time in minutes, but with bacteria growing, and they're saying to look at this data and write a power regression equation. Okay, power regression for this set. And we're going to round to 3 decimal places. So let's go back to our calculator. I'll do this one with you from the start. So if we go to the calculator, okay, we're going to go into our stat menu, go to edit, so hit enter. Now we have data in here, so the quickest way to kind of erase it is to go up to the list and hit clear. Now it doesn't look like it did anything, but then if I hit enter, I get down into my list. You don't want to hit delete, because delete will actually delete the whole row out of your calculator, and then you'll have to go back and get that list. So just clear, enter. I'll do it again when we get to L2. So I'm typing in my minutes, 1, 3, 5, 7, 9, and 11. And then if I scroll over and go up to the top, go to L2, hit clear, enter. I'm going to type in my number of bacteria. So 2, 25, 81, 175, 310, and 497. Okay, now we're going to go to stat. We're going to go to calc, and we're going to go find power regression. Okay, choice A. So let's hit enter. Again, X is in L1, good. Y is in L2, awesome. You don't need to do anything else except calculate. And for power regression, they're giving us here that it's A, the leading coefficient, which is about 2.0087, times X raised to the power of B. So let's go back to our notes. Okay, so I had A was 2.000877. B was 2.298056. And the equation is y equals A times X to the B. So we're going to round to 3 decimal places. So y equals 2.001 times X to the 2.298 power. Okay, so that's all we have to do for this first part. And then the second part says use this equation to predict the bacteria's growth to the nearest integer after 15 minutes. So this is an X value, so I'm just plugging in. So y equals 2.001 times 15, which is my x, raised to the 2.298 power. So I'm just going to type that right into my calculator, multiply it by 15, raised it to the 2.298, and we should get 1009.03168, but they want me to round to the nearest integer, so after 15 minutes we have 1009 as our number of bacteria. Okay, that's the end of the video for today. All you're doing now is completing the notes for this. Make sure you